Alright, now we come back and we finish with one final topic, although we'll do a couple problems. Newton's law of cooling. The rate at which an object's temperature is changing depends on a variety of things. Temperature that it starts out at, the surrounding temperature, and so on. Now what Newton determined in this is he came up with this equation. If T is the temperature of the object at time T, and T sub S is the surrounding temperature, then the rate of change can be found by this equation here, where K represents some constant of change. He then solved this differentiable equation. It's a separable differential equation. He ended up with this equation down here. Let me move the screen down. This equation right down here is considered to be Newton's law of cooling. Where again, T sub S is the surrounding temperature. So imagine an object and the temperature that's surrounding it. T naught is the starting temperature, and again K is a constant, and T is time, and then this T right here represents temperature at some point in time. So let's do an example using Newton's law of cooling. Hard-boiled eggs at 98 degrees Celsius, puts in a pan with 18 degrees Celsius water to cool it. After 5 minutes, the egg's temperature is 38 degrees. How much longer will the egg take to reach 20 degrees? So we'll start with the law of cooling right here. Now, what do we know? We know that the starting temperature is 18. That's T sub S. We know that, the starting temperature T sub naught was 98. The surrounding temperature T sub S is the water that surrounds the egg. That's 18 degrees. And let's simplify this just a bit, and we end up with this right here. Now, we know that after 5 minutes, the temperature of the egg is 38 degrees. Now I can plug those two values in and I can use that to solve for K. So 38 minus 18 is 20. Divide both sides by 80, you get 0.25 e to the negative K5. Natural log of both sides to get rid of the e. Divide by negative 5, and we have this. Now, again, the 5 goes to the bottom, but just like we did in an earlier problem, this 0.25 is 1/4. Well, 1/4 is 4 to the negative 1, and that negative 1 can come out front. As it's an exponent, it can come out front, and that negative cancels that negative right there, and that's how we get this. So here now is my updated formula. T minus 18, the surrounding temperature, equals 80, which remember was the combination of starting and surrounding, e to the KT, and there's our K value. If you're wondering perhaps where this negative came from here, it came from this negative right here. It's not that we just arbitrarily slapped one on, it's because of this negative here. Now, what do we wanted to know? We wanted to know when is it going to be 20 degrees. So I'll plug in 20 for T. 20 minus 18 is 2. Divide both sides by 80. We get this when you do that. Natural log of both sides. And then to solve for T, we'll take this and divide by the negative natural log 4 over 5. So that divided by this. And that does give you about 13.3 minutes. Now notice it said how much longer. Alright, how much longer? Well, at 5 minutes past, it was 38. At 13 minutes, it's down to 20. So how much longer? Well, if I'm going from 5 minutes to 13 minutes, that's 8 extra minutes. Now, we can also utilize our graphing calculators to do Newton's law of cooling, and I have seen a problem like this on the AP exam, at least on the review packets that we get. So let's consider this. Temperature probe is removed from a cup of coffee, placed in water that has a temperature of 4.5 degrees Celsius. The readings below, the table below are the readings of the temperature probe as time is passing. So after 2 seconds, the probe has heated up to, or is cooled down, I should say, to 64.8 degrees. After 5, 49 degrees, 10, 31.4, and so on, etc., etc. And what are we going to do? It says estimate A, the coffee's temperature, after it was removed, and then B, the time when the temperature will be 8 degrees. So we need to come up with those two things. Now notice we've got this column over here, this T minus T sub S degrees Celsius. The reason that is, if you go back and look at Newton's law of cooling, the left-hand side is the t minus t sub s, but the right-hand side really looks like an exponential equation. Just look at the right-hand side. Now, if you can imagine combining things together, specifically look at the last problem we did when we had simplified and combined, that right-hand side looked like an exponential equation. So what I'm going to do is I'm going to take my calculator and I'm going to ignore this right here. And if you're wondering how I got these, it's this minus 4.5. Remember the temperature was 4.5, so surrounding temperature was 4.5. And I'm going to take this for my x's, I'm going to take this for my y's, and I'm going to put that into my calculator, and I'm going to do an exponential regression. So if you want to pause the video now and do that, you can. This is what I got. Now the calculator actually gives me this part right here, 61.66, 0.9277 to the t. That is an exponential regression. And so t minus t sub s. Now I know what t sub s is. T sub s was 4.5. And now I can solve for t, and I have this equation here. 4.5 plus 61.66 times 0.92277 to the t. Now again, estimate the coffee's temperature at the time the temperature probe was removed. That was the first thing. So when was the probe removed? It was removed at time 0. So we plug in 0 for t. This becomes 1. And I'll take the 4.5, add it to the 61.66, and that's how we get this. So at the exact moment the probe was removed, the coffee's temperature was 66.16 degrees Celsius. In part B, the time when the probe will be reading 8 degrees, I'll plug in 8 for t. Subtract the 4.5 over, divide by 61.66, and I'll take the natural log of both sides, although again you can do log of this base right here, 0.9277 if you wish. And then I'll divide, and then that gives me a t value of about 38 seconds. I hope we didn't go as fast in this video, but if you do have any questions, feel free to ask me tomorrow in class.